So let's go ahead and watch that. NASA is with you when you fly. So NASA's with you when you fly. So whenever you think about flying, a lot of people don't realize that a lot of NASA technology is in the plane that you're flying on, especially the winglets. If you've ever looked at the end of a wing and there's a part of it that's flipped up, that's called a winglet. That's some NASA technology that we learned about and shared that. So we're going to talk about Bernoulli's principle. We'll talk about the applications of flight, in particular, a NASA project called ACTE, the Adaptive Compliant Trailing Edge Flight Experiment. We'll talk about soccer balls, and then also other activities exploring the Bernoulli's principle. The overview, and this lesson overview really works out well if you've got a lesson plan that you've got to fill out. This just kind of gives you an idea about the lessons that go with that. Same deal with the student will be able to explain why air is a fluid similar to water, demonstrate how the Bernoulli principle helps create lift, use a scientific method to predict, observe, and conclude, and then also explain the relationship between the velocity of a fluid and the amount of lift that's created. Yes, at the end of today's session, you will be able to download both my PowerPoint and a copy of the Bernoulli's activity guide. So these NGSS standards, again, I've just included those so that if you've got to do a lesson plan, those are easy to grab and include. There are several different connections within the NGSS standards, both connections to the nature of science, as well as energy technology and applications of science. So who exactly is Bernoulli? Which, it's kind of a funky little name. Well, he's a Dutch-born scientist, but he studied in Italy. His family are renowned mathematicians. His dad was an earlier developer of calculus, and his uncle Jacob was one of the first to discover the theory of probability. And what I love about this next bullet is that I think sometimes our students can identify with parental expectations because Daniel's dad insisted that he study business and then medicine, which Daniel did, and he did so with distinction. But mathematics is what really captured Daniel's interest and imagination. And the combination of that is really what helps us to understand Bernoulli's principle. In 1738, yes, that's a long time ago, he published a book. He published I don't know that it was so much a book, but it was a study of his fluids on dynamics. It was called Hydrodynamica, and explained how fluids behave when they're in motion. And so as a fluid moves faster, it produces less pressure. And the converse of that is true, which is that slower moving fluids produce greater pressure. So with that, we have to first understand what exactly is a fluid. A lot of times whenever we think about, well, what's the state of matter, we'll think, okay, so there's solid, liquid, gas, and plasma. So what exactly is a fluid? Well, fluid isn't a state of matter. By definition, a substance that is capable of changing shape at a steady rate when acted upon by a force is considered a fluid. And so that includes both liquids and gases because they both flow and they both change shapes. And when I taught in the classroom, I would often have a um, balloon filled with water as well as a balloon filled with air, not completely full, but if you know the balloons you can get that you can shape into animals, that's the type that I did, and I didn't quite put them full so that students could twist them and push them so that they could literally see how that the fluids, you can't see my air quotes, but flowed. So understanding what a fluid is a big deal. So, and with Bernoulli's principle comes in the aspects of both pressure and velocity. And when looking at a moving fluid, they are inversely proportional, which means if the pressure is high, the velocity is low. And if the pressure is low, then the velocity is high. So in essence, the pressure of a fluid decreases as the fluid's velocity increases. Now you'll notice in the lower right-hand corner it says paper demo. If you were to get a sheet of paper and hold it up in front of your lips and blow out over top of it, most people would expect the paper to go down because you're blowing down on it. But what actually happens is because the fluid, the air moving over top of it is moving faster, it actually causes a decrease in pressure, causing the paper to rise. So even though you're pushing down on the paper with your air, with your breath and breathing, it actually causes it to rise. So again, it's a cute, quick little demonstration to blow across the piece of a paper. But we actually have a demo of this. And what you're looking at in this picture is this right here is the cross section of a wing. And it's showing you that as the air goes across it, that it creates the lift. And so we will take a look at that. So as you've got the cross section of a wing there, the faster air produces a lower pressure, sucking the wing upward. And this typical shape of the wing is called an airfoil. So that cross section of that airfoil or the wing causes the air to move over top of it to travel faster than what's going underneath. And if it's traveling faster, then it's a lower pressure. Slower, then it's a higher pressure. And so with Bernoulli's law, this faster moving air on top has a lower pressure than the bottom. And due to the pressure difference, the wing is being pushed upward or it's lifted against gravity. So there is a cool video from the University of Cambridge that talks about, or actually doesn't talk about, it shows how wings work, and it uses smoke streams around an airfoil, which is again the cross section of a wing. And so I'm going to play that here, and you'll be able to see the airflow and the smoke streams around the airfoil. And again, an airfoil is simply the cross section of an airplane wing. So in this one here, they have pulsed so that you can actually see that as it meets the front of the wing, that the air particles on top tend to move faster than those on the bottom. And that has to do with the shape of the airfoil. But because of that, if it's moving faster, then that means it's creating less pressure. And if it creates less pressure, then that means it's going to lift up off of the ground. They also in this demo talk about the angle of attack. And while we're really not talking about angle of attack, I think you can still understand the disruption that an angle of attack occurs. So you can see this is kind of smooth, but as that angle of the airfoil or wing changes, you can see how at the back of the plane, the air particles are just horrible. And this actually creates what's called a stall. When the air particles don't come back together the way they're supposed to, you get a stall and there's a sudden loss of lift. So there's no longer a process. So if you've seen the NASCAR racing at Talladega and they talk about getting up close behind a car, they call that where the flow is attached. That means that the air particles come together. And then you can see here the big empty part here. So this, just a second, let me pause this. This has the flow attached because you can see that it comes back down. But as it continues to move, right here, the flow is no longer attached. It's not going down, it's going straight out. And that's what causes a stall. Or if you're in a car driving very fast, like at Talladega, where aerodynamics matter, if you take the air off of somebody's bumper on Talladega, it's going to create lift and could potentially cause them to wreck or spin out, which is one of the reasons why they have flaps on the car, so that if the car does go airborne, those flaps can go up and help to keep it from flying. So lots of aerodynamics involved whenever we're looking at Bernoulli's principle. And I know I said a soccer ball, but we're actually talking a little bit about cars here. And what I love about talking about soccer balls and cars is that in a science class, you start talking to kids about cars and sports balls. You get a non-traditional student that maybe is a little bit more interested in science because, hey, I play soccer, I play football, I play baseball. These things make sense to me, so making those connections to life are always nice. Air slows cars down a lot and makes them lose energy. Cars were designed with smooth lines like fish to help them cut through the air. Engineers test car designs in wind tunnels to see how easily they cut through the air. And I'll say that in looking at aerodynamics, it's not just going through the air. Whenever you think about Olympic swimmers, they pay attention to their uniforms and how they flow through the water. And you don't typically see hairy swimmers at the Olympics because that hair slows it down. And you're like, but how much does, arm hair, leg hair really slow down a swimmer? Well, whenever you're talking Olympics and hundreds of thousandths of a second matter, they do everything they can to get that competitive advantage. So on to the NASA activity, the NASA project called ACTE, Adaptive Compliant Trailing Edge. ACTE, the goal was to determine if using flexible trailing edge wing flaps could improve the aircraft's aerodynamic efficiency, as well as reduce the noise generated during takeoff and landings. And if you've ever been in an airport, when a plane takes off and it lands, you can definitely hear it. Is this going to be shared after the session? Are you referring to my PowerPoint, Miranda? Because if that's the case, yes, you'll be able to download. So yeah, yes, you'll be able to download, provided you are on a computer. And if you're not on a computer, I'll leave it up to where you can get to a computer and come back and download later. So for this particular project, NASA took a G3, a Gulfstream 3, which is a very common business aircraft, and they converted the back side of the wing, we're seeing here at the back, and they converted that into they used a Flexus system. And we're going to take another look at that from a different perspective. And let me show you a video about that. Here's the link to that if you need it. And so they retrofitted it with flex foil. And here's a video about that.
More than 100 years ago, the Wright brothers designed and built the first successful airplane, twisting the wings to control the aircraft. Soon after the inaugural flight, Curtiss improved the original design with the introduction of hinged flaps, quickly adopted by all aircraft designers. Achieving seamless control surfaces rather than hinged flaps has been an elusive goal for decades. Today, however, the aerodynamic efficiency goal has been achieved. Flexus pioneered the compliant design technology, enabling monolithic elastic structures to be strong, flexible, and seamless. The simplicity of jointless elastic structure developed by Flexus enabled the creation of lightweight, reliable, and cost-effective variable geometry control surfaces. Using well-known aerospace-grade materials and actuators, Flexus has integrated their technology within existing aircraft architecture. The Air Force Research Labs conducted extensive testing with Flexus to confirm aerodynamic efficiency and structural integrity of the variable geometry design. In July 2014, Flexus, in partnership with the Air Force and NASA, will be flight testing a Gulfstream business jet retrofitted with FlexFoil seamless control surfaces. The benefits of this design, the ability to twist and change the camber of the wing, allow an aircraft to attain the sweet spot of current operating conditions in flight, including fuel savings of 3 to 5% on a retrofit and 8 to 12% on a clean sheet build, along with significant noise reduction during takeoff and landing. Flexus technology has many other applications, such as variable geometry leading edge, engine inlets, helicopter rotor blades, ships, wind turbines, and hydrodynamic surfaces or fluid pumps. The performance of any object moving through a fluid medium can be maximized through Flexus variable geometry technology. What can you do with this technology? We invite you to consider the possibilities. Flexus, engineered to flex.
So NASA, in partnership with the U.S. Air Force as well as Flexus, took and modified that G3, and this is the trailing edge, and they did it on both sides of the airplane. But you can see this section here where they replaced those flaps and put that flexible system in. And they took the conventional 19-foot long aluminum flap and put in the flexible ones. And then from that, here is a photo of NASA actually testing that. Again, I'm putting the video link in the chat. Whenever you get the PowerPoint, all of the video links will be there. Don't feel like you need to take care of those. I will stop right here and see. If you see, it looks like little pieces of yarn on the flap there. Those are fiber optic sensors so that they can test while the plane is flying. Each of those is a data point that they can gather data from regarding the stress and strain that's on the wing from that, which I just think is absolutely.
Here's the checklist for we're taking off probably in about 5 to 7 minutes. Copy that, NASA 804, hold NASA 850, and proceeding at clock now. Coming left, control, here comes your left-hand turn for the phasing.
And go ahead, 804, 10 knots.
All right. And in answer to Amy's question, yes, anything that I'm sharing, you are more than free to use. It's already been paid for by taxpayer dollars, and so by nature, it is a free to the public. So I mentioned earlier about soccer balls, and so I didn't know, and when I first started, that there were different types of soccer balls and different designs, but there are, and so I'm going to show you a couple of videos. And if there's any math teachers out there, there's some phenomenal about the platonic solids that are here that are just amazing. So here we're going to take a look at the soccer ball.
Since
Aerodynamics
1970,
that goes with it.
Adidas has been designing the balls for the FIFA World Cup. Our question: what does mathematics say about these designs? First, we need to understand the 5 platonic solids: the tetrahedron, the cube, the octahedron, the dodecahedron, and the icosahedron. Each of these solids has congruent faces. For example, the cube has 6 square faces, and each corner is met by 3 edges, while the icosahedron has 20 triangular faces, and each corner connects 5 edges. The structure of the World Cup balls are each based on one of these platonic solids. The Telstar, introduced in 1970, is the classical design with its 12 black pentagons and 20 white hexagons. It's not a platonic solid, but it's one step away. Start with an icosahedron. Pick a corner, divide its connecting edges into thirds, mark a pentagon, then cut off the corner. Doing this to each of the 12 corners creates 12 pentagonal faces. Pumping it up produces the Telstar. Now look at the next 8 World Cups: the Telstar Durlast, the Tango España, the Azteca, the Etrusco Unico, the Questra, the Tricolor, and the Fever Nova. Although they have different printed patterns, the physical panels with 20 hexagons and 12 pentagons is the same as the 1970 Telstar. This all changed with the 2006 Teamgeist in Germany. It has 6 dumbbell-shaped panels and 8 propeller shapes. Unlike the Telstar's panels, which are stitched together, the Teamgeist panels are thermally bonded. This ball received criticism because of its erratic flight. How is the Teamgeist made from a platonic solid? Start with a cube. Like before, pick a corner, divide the connecting edges into thirds, then slice off the corners. Doing this to each corner produces the truncated cube with 6 octagons and 8 triangles. To get the Teamgeist, identify each octagon with a dumbbell-shaped panel and each triangle with a propeller shape. Reshaping the panels and inflating it produces the Teamgeist. And don't be fooled by a fake Teamgeist, which prints the Teamgeist pattern onto a Telstar design. In 2010, the South African World Cup introduced the Jabulani. While a casual look suggests that there are many panels, there are really only 8. 4 round panels and 4 propellers. This ball was also criticized for beach ball-like flight, possibly due to its shallow seams. For its design, start with the tetrahedron and truncate the 4 corners to produce 4 triangular faces and 4 hexagonal faces. Identifying the triangles with the ovals and the hexagons with the propellers, then reshaping produces the Jabulani. This brings us to the 2014 Brazuca debuted in Brazil. Named by the fans, this ball has only 6 panels, the fewest yet. These 6 propellers correspond to the faces of a cube. The propellers don't overlap, just like the faces of the cube don't overlap. You can also see this connection from the seams. 3 seams meet at a corner, just like 3 edges meet at a corner of a cube. Reshaping the squares into the propellers produces the bazooka. So with all of these different balls, which one is your favorite?
I mean, who knew that there was so much into a soccer ball? I didn't. But the aerodynamics and how things fly, those come into account, and NASA takes a look at them. This here is a scale model of that 32 panel ball, what I consider a traditional soccer ball, up at Ames Research Center in a water channel. Now the green dye shows the water flow around the soccer ball, and that pink dye is actually injected separately behind the ball to be able to see the low pressure zone and how that affects. And you can see the flow is connected. But anyway, so just some really neat things whenever you think about beach-like ball, erratic behavior. The same thing could be said in baseball, in a pitch with a knuckleball. It's kind of got that erratic flying behavior. And so understanding those things, really, really makes a difference. And this next video is talking about actually taking the World Cup ball into a NASA wind tunnel. And I played the first one to help you understand the different types of balls and how they're made. But then the second one here talks about how that NASA.
Aerodynamics basically is the study of fluid flow around objects. NASA is not in the business of designing soccer balls or any balls for that matter, or testing them. What we do use sports balls here, especially in our lab, is for educational purposes. We found that it's very easy to get young kids interested in our field by showing something they can relate to. What we have here is a wind tunnel, which is basically a chamber through which air flows. When it comes to soccer balls, what we're looking at is the flight of the ball through the air. There's a very thin film or layer that forms near the ball surface, and it's the behavior of that layer, which we call a boundary layer, which is critical to the performance of the ball. As far as the aerodynamics go, it's the structure of the outside, the material, the roughness. That's what determines the aerodynamics of the ball. Knuckling is when the ball flies erratically through the air, or it may change directions as it's flying through the air. What's been done to the bazooka is that by using these panels with fingers on it, the seam length has been increased compared to the ball in 2010. What we're looking at with the smoke patterns is where does that smoke leave the ball, at what point along the surface. And when that position of that separation location changes suddenly, then that is the speed at which the ball will knuckle the most. I think the basic message for the players is that I think you'll see less of this knuckling effect. They'll find that it behaves more like the traditional ball, and I believe they'll be happier.
And I hope that you saw during that what they were talking about there with the knuckling of the ball and how that relates back to the baseball. So just really cool to think about all those different types of ways that we can relate to the real life of our students, talking about the aerodynamics of a car, talking about a sports ball. So on to the activities and talking about the Bernoulli's experiment log. So with experimenting with Bernoulli's, there's 5 different activities. There's a paper tent, magic soda cans, balancing balls, levitate a spear, and cup of water. And so on all of those, we have where they predict or reflect what they think will happen. Then they do an experiment. They actually do the experiment. And then from that experiment, they can then take a look at what actually happened. And then after it has happened, then they can reflect, what is it that what I said and how that relates, and then does it, does it fit, So I think that works really great for the students to be able to do that predict or preflect, and then experiment and observe. And then I just uploaded, I don't always do this, but I did for this one, where you can see, if it'll stop moving. This is that Bernoulli's experiment log. And so you can see there's 6 different options. Now, I know I've not told you what each of these things are, but if you'll give me a second, I'll give you that. So the paper tint, normal, and then increase, the magic soda cans, cup of water, levitate a sphere, and balancing the cheese ball. And so for the paper tint, your students are going to take, so students get a straw, and I will say, you have to be mindful in this day and time of COVID about, using a straw and you're asking students to blow. So just, be mindful of that, as I know you are so many different things in the classroom. But you basically take one piece of paper, if you'll think about like an index card, and make a little tent out of it, and then they blow through it with the straw, and they have to observe what happens. And most people think that the tent's going to blow away. But Bernoulli's principle states that the faster a fluid moves, the less pressure it'll exert. So as you blow in between under the tent, it produces faster moving flow, which means it's less pressure, and that causes the tent to actually suck down to the table. And then between two soda cans, and you blow between them, again, they're about an inch apart. The same process happens. A lot of people think those cans are going to go blowing somewhere else. Well, no, what happens is that pressure decreases and they actually suck together. If you've ever been on the interstate and saw 2 tractor and trailers passing each other, and it looks like that their trailers are kind of tipping in towards each other, that's Bernoulli's. If you've ever sat at a stop sign and had someone pass you extremely fast, and all of a sudden your car starts moving, that's Bernoulli's. It's that. I guess one for me is like where growing up in the summer we didn't have AC, and so I had the door partially open, and a good burst of air comes through. And as the air comes through, the faster it flows, the less the pressure, and all of a sudden the door slams shut. That's Bernoulli's. And so you can also do this activity with water bottles, assuming that, there's not many ridges. You just want them to be close enough that they'll go together. This one here, balancing the cheese balls, this is where it helps to have the flexible straw. The roundness of the cheese ball really does make a difference. The rounder it is, the more aerodynamic it is, the easier that is. I will say, especially with your middle school students who can be very competitive, remind the students to breathe, because in breathing through that straw, trying to keep that cheese ball up as high as possible, they'll run out of breath. I had some educator, and I had a couple of educators that were competing against each other, and one of them almost passed out because he wasn't breathing. He was sending all of his air through the straw, and he just got lightheaded. So please be mindful of that. You can use styrofoam balls. If you get the little ones, they just tend to be a little bit more expensive than the cheese balls. And I had somebody says, "Oh, you could use a ping pong ball," because a ping pong ball is perfectly shaped. The problem is that a ping pong ball tends to be heavier than a cheese ball. And with it being heavier, that means you have to produce more air. And I will also say that the size of the straw you use matters. The smaller diameter the straw is, the longer your air will push through it. Obviously, the bigger it is, the faster your air will go through it. The next activity is levitating a sphere. And so as you can see here, they've got funnels, and you put the ping pong ball in the funnel. And I will tell you, having many years provided the supplies for science things in my classroom. I don't use real ping pong balls. I go on Amazon and I get 144 beer pong balls, because a ping pong ball, once it's dented, you can't do anything with it. The beer pong balls are not as rigid, they're not as heavy, and they tend to last. They're more durable in dealing with students. Now, I will absolutely say that I don't ever tell my kids that they're beer pong balls. They're just a cheaper version of a ping pong ball, because once a ping pong ball gets flattened, you're just kind of stuck with it. But if money's not an issue, then yes. But I tend to use the cheap ones off Amazon. The other thing is with the funnels. If you've got funnels, that's great. But if you don't, you can also take a 2-liter bottle, and the 2-liter bottle, if you'll think the cap being here, and then where the shoulder comes out, just let that shoulder come down a little bit and then cut that off. And you can always take a little file or a piece of tape and go around it. And so one aspect, you have the person that is blowing up through the straw, blowing up through the funnel, and then the one here is you're blowing across it. And so again, allow the students to see that. And then this last one, let me just go ahead and hide this. I've got these all within the PowerPoint as well, but I didn't have a picture of the log. So with the cup of water, and this is typically the last activity you let your students do. And the reason it's the last activity is because you've got to cut the straw in half. And so you've got one piece of straw that's in the water and one piece of straw that's out of the water. And depending on how wet you want the kids to be, what happens is as you blow over the top of the straw, you decrease the pressure, and that causes the water to rise up in the straw. And if you get the water to rise up high enough, you can actually blow the water out on the person sitting across from you. I love this activity. And you can also hear the difference in the pitch as the water height changes. You can tell a difference based upon the length of the water column that's there. So again, you have the students do the preflect or predict what they think will happen. Now, I require my students to have that completed. I don't let them work in a group on that. Every student completes their own Bernoulli experiment log. I don't care if they want to talk about it, but they've got to write it down themselves. And I don't give them the materials to go do the experiment until they have completed the preflection. A lot of students don't like it whenever they get their preflection wrong, but the good part is that, if you get it wrong, then you get to talk about a reflection or a conclusion. If you get everything right, it's kind of hard to reflect on, well, I already knew all that. So, but anyway, so any questions about that or any of these as I've talked about them? Okay, seeing none. This next one that I see Peggy's typing, so I'll wait and see what Peggy has to say. Okay, I see a couple people typing. Yay. Yes, I do. Peggy, I do. I show them, I use these slides right here and I talk them through them. And then I also somewhat demo for them, but I don't demo it enough that they can go ahead and predict what's so great question. Looks like a lot of fun. Kimberly, it really is. It really is. Okay, so this next video that I'm going to show you is actually from on board the International Space Station. And it's a 7-minute video, but I'm going to show you the whole thing because it is so totally worth it. And so I'm putting the link to YouTube. So if there's something wrong with the video here, then you can go there to watch it.
Hey there, Welcome to NASA Launchpad. I'm your host, Vince Whitfield. Check this out. Today we're going to be talking about how this works, and some other cool stuff Bernoulli did. Oh, that's Daniel Bernoulli, the Dutch-Swiss mathematician known for, that's right, the Bernoulli principle. Remember Bernoulli's principle? If you don't, that's okay. Let's check in with JAXA astronaut Koichi Wakata and ESA astronaut Frank de Win on board the International Space Station to review this principle with us. And let's see how Bernoulli's principle can be demonstrated from space.
In a fluid flow, when the flow gets higher, the pressure decreases. And this fact is now well known as the Bernoulli's principle. If you apply this principle in a fluid flow, in a closed system such as water flow in a tube, if you imagine the tube gets bigger and narrower, the pressure actually decreases when the speed gets higher. And when the speed of the water gets slower, the pressure actually increases. One of the examples that I can give you is that think about the garden hose. And if a water is coming out from the garden hose with a maximum speed, if you still want to increase the speed of the water coming out of the garden hose, what you're going to do is you're going to put your thumb onto the exit of the hose. By doing that, the speed of the water increases, and at the same time, the pressure of the water decreases.
You heard Koichi Wakata talk about water in a garden hose. And yes, Bernoulli's principle deals with fluid. But here's an important thing to keep in mind. Fluid doesn't necessarily mean liquid. Fluid is a generic name that applies to substances that behave in certain ways. Fluids flow smoothly and around things, so gases can be fluids, as can plasma, and even to some extent, plastic solids. Let's take a look at another demonstration of Bernoulli's principle, this time showing how it can apply to a gas, like air.
We are placing these containers not so far from each other, about 5 to 10 centimeters. And then Koichi is going to blow in the middle of those two containers. What do you expect that will happen? Because he blows in the middle, the containers are going to move away from each other, or if he's blowing in the middle, the containers are going to come together. Let's have a look. What you can very easily see here as the containers are drifting together. What is happening? Again, the air that Koichi is blowing through the containers has a higher velocity than the surrounding airs. Because of that, the air traveling in between the containers has a lower pressure because it's moving at a higher speed. Because of that, the pressure on the outside is pressing the two containers together. You can also observe this when you're driving on a highway. When you get too close to a truck, for example, that is driving next to you, automatically you will be drawn towards that truck and you need to steer away from the truck. So this is one of the examples as well of the Bernoulli principle.
Guess what? You don't have to be on the ISS to try this demonstration. Oh sure, your food containers won't stay suspended in mid-air on Earth like they did on the ISS, but try this demonstration with two balloons hanging close to each other. These balloons are hanging from string taped to a doorway. What do you think will happen when you blow gently between the balloons? That's right, they are pulled together. The air moving between them has less pressure than the air on the other side of each balloon. So, they're pushed together. Here's another example that works on Earth and in space. Watch Frank's demonstration with a piece of paper, and then try it yourself.
Right now, what Frank has a piece of paper. It's curved. And what he's going to do is now he's gonna hold this paper, and it's curved, and he's gonna blow on the top surface of the paper. What do you think this paper will do? Since the paper is curved like this, do you think the paper will come down or comes up? Let's see what happens. As you see, when Frank blows air on the top side of the paper itself lifts up. This is again one example of the Bernoulli's principle. The air that goes on the top surface of the paper has a higher velocity than the air that is underneath the paper. Because of that difference in the velocity, the pressure of the upper surface has a small pressure than the lower surface. As a result, the paper is lifted up. This is a principle, of course, that I have used a lot in my previous career because I used to be a pilot. And this is how airplanes fly. If you look to the wing of an airplane, you see that it's curved, always a little bit towards the bottom. The side on the top side is longer and is more curved than the bottom side. This means that the air traveling on the top of the wing will travel faster than the air underneath the wing, creating a lower pressure and lifting the wing up. This is what we call lift. And because of this lift, we can travel and we can fly all around the world. Not only me, but you as well can travel wherever you want thanks to the Bernoulli effect.
So there you go. When you increase the speed in a stream of fluid, remember that's both liquids and gases, the pressure of that stream decreases. Pretty cool, huh? Bernoulli's principle relates to everything from spraying your best friend with a hose to flying in an aeroplane. There's actually more than Bernoulli's principle involved when you take off in an airplane, but that's another topic for another NASA launch pad. Well, that's it for now. Special thanks to our on-orbit astronauts. Until next time, I'm Vince Whitfield. Thanks for watching NASA Launchpad.
So much information there. I just love it. And Koichi Wakaka is he's a Japanese astronaut, and he's actually currently on the International Space Station. So if you show this video to your students in the next 5 months, you can say that he's currently on board the space station, because I think he's there for a 6-month rotation. So just absolutely amazing. Earlier, I talked about the paper demo, and they showed that during that video. I've done really good tonight in terms of getting through the materials, because normally I don't get to show that entire video. So I'm very excited about that. So I'm glad that you could see the, and just like they talked about with the 18-wheelers and the way he took the 2 different cases, that's what you're doing with the soda cans. So to have the students do the activities here on the ground with what they've done in space, and whether you choose to show that video prior to doing the activities or after doing the activities, that's totally your choice. I think a lot of that depends upon the type of class that you teach. I know I sometimes had a physical science class and an honors physical science class. For an honors physical science class, there's no way I'd show that video to begin with. I would show it afterwards. But with a general physical science class, if students really struggle with the topic of Bernoulli's, I may show that to begin with before we do our activity, just so that they can help understand it a little bit more. And you know, but I mean, that's just ways that you can change it within your classroom with FIT. I included this slide here because when I'm actually doing the activities, I actually have the students come and report out. But we are at the end of our session.